They discovered GPU. The vast majority of those employees, of those contributors, work at Nvidia. And when I saw that they were taking the GPU and they were using it for general purpose floating point mathematics, in fact, is it possible for us to create a new class of processors that is completely general purpose, programmable with C, programmable in new modern computer constructs, but does not have the personality, does not have the characteristics, and potentially does not have the limitations of a CPU. That we would design a processor whose architecture is so different than a CPU, not to replace the CPU, but to work with the CPU. Why replace the CPU? It's a marvelous piece of engineering. It has taken us 25 years to achieve that. Hundreds of billions of dollars of R&D has gone into that CPU. Why replace it? Let's build something to work with it, to supplement its weakness. And we know that the CPU has several weaknesses. We know that no matter how large the cache is, it's never big enough. So why don't we design a processor that is a fundamentally cache-miss architecture? We also know that one of the limitations of the CPU is when you add more cores, the bandwidth of the cache is shared by all of the CPUs. Which means the more cores you have, the less the cache capacity and the less the cache bandwidth you have, which is odd. This is the only feature in the history of computer design. And so we said, why don't we design an architecture that more cores is just more cores? If you have one core, you have one performance. If you have two cores, you have two performance. More cores is more cores. And so it's a cache-miss architecture. It has many, many cores. Today, it has 240, 256 cores. Tomorrow, it will have tens of thousands of cores. And so the question then becomes, what would you do with an architecture like this? And how do you create a programming construct that people can understand? How do you create a construct that people can relate to? And how do you apply it to the right problems? And so that's where the invention of CUDA started. It started from the recognition that we don't want to replace the CPU, that we want to create a heterogeneous parallel computing architecture, that the right things should be run on the CPU, which is a lot of code in the world, and the right type of applications and the right type of code could be offloaded to the GPU, and the performance should be several hundred times faster. Notice, there are very few people in the world who are doing 4-core design. And the reason for that is because it's only 1.5 times faster than dual core. And if it's 1.5 times faster, we know what the answer is as an engineer. Wait. In 2 years, because that's how long it will take me to finish it, and QA and so on and so forth, dual core would be 1.5 times faster already. And so we realize we cannot just be 1.5 times or 2 times faster, that we have to be many hundred times faster. And so the programming model had to promise that it's not extremely easy to use. It's not impossible to use, because it's in a programming language you understand. But it's not extremely easy to use. Extreme easiness was not its purpose. The ability to promise 50 times, 100 times speed up was its promise. That is its first objective, because ease of use is already achieved. It's running on a CPU, C++, Visual C++. It's already been achieved. We cannot achieve better than that. The only thing we can do is achieve more performance than that. About 2 years ago, and we made another decision that was really a good one, but expensive one. On the day we announced CUDA, we had some benchmarks, we had some demos, we had some SDK, but there were precisely 0 applications. And it's expensive to put CUDA on our GPUs. We decided that in order to create a computing platform that is useful to the world, the installed base has to be high. The installed base has to be high. So we know we could not build a separate processor that you can buy if you want CUDA processing. We realized the first thing we had to do was do our job. Put it on every single chip, guarantee that it's compatible, offer it from top to bottom, any GeForce, and make sure that we ship millions and millions of them. Today there are 80 million CUDA processors in the world, 80 million. It is available from every single personal computer OEM in the world. It is on notebooks and desktops and workstations. You can buy it in retail, you can buy it online. It is impossible to not find CUDA. This is a fabulous story. So I was in Japan last time, and a professor walked up to me and was telling me that in his career, this is an old man, he does supercomputing research. He walks up to me, he says, in my career, I've had 2 surprises. Do you guys remember that conversation? He had 2 surprises in his career. The first one was the Cray supercomputer. The second one was a student who told him, you can achieve several hundred times speed up on a video game card. But you have to go down to Akihabara to buy it. Well, to his surprise, he already had it in his computer. He just had a GeForce. Downloaded CUDA, he wrote his application, he's doing plasma research, computational fluid dynamics, and as you know, computational fluid dynamics is a type of structure that is extremely fast to parallelize. He saw 200 times speed up. He could not believe it. He thought he programmed the chip wrong and that the answer was wrong. But it's IEEE compatible, 64 bits. You can compare the answers with your CPU. He realized it was the perfect answer. It's just 200 times faster. The CUDA programming construct, although not easy to remember, not easy to learn, it is not impossible to learn. And the programming benefit is several hundred times speed up. Now the question is, what can you use it for? This is the Nvidia website in Japan, in the United States. And if you go to CUDA Zone, you will see there's currently 100 examples of real applications that have been written on top of CUDA. This is now applications a day. Every single day, new applications are being posted on here. And you will see examples of what other people have done with CUDA. And on the bottom, this is great. The efficient computation of some products on GPUs, 270 times speed up. Acceleration of fault simulation, 35 times speed up. Science finance speeds financial results on parallel computing, 80 times speed up. Low viscosity flow simulation, oh, that's a good one, 55 times speed up. There's astrophysics. There's computational finance. There's computational biochemistry, fluid dynamics, finite element analysis. It's unbelievable. Now it's just happening all by itself. Now for one of the particular fields, CUDA, you must know, is extremely fast, which is image processing. Because GPU is fundamentally an image processor, and we've turned the GPU into a programmable image processor. If you have an image processing application, and it literally takes 1 minute to do the filtering, and now it takes a couple of seconds, I'm not surprised. I think you will be surprised when you really use CUDA, how much speed up it has, and I think your first impression is, you made a mistake. That is the first impression of most people who program CUDA, that my program is wrong. I've ported it wrong, I've missed an entire loop. That is the first impression. So I hope that many of you will have that surprise. I'm really, really glad that you guys are here today. It is a great honor for us to spend time with you. CUDA, I believe, is going to be, when everybody looks back 10 years from now, and maybe when I look back on my career, CUDA will be the single greatest contribution we've made to the computer industry, bringing heterogeneous parallel computing to the world in a way that the world can use it is probably going to be our greatest contribution. Enjoy yourself today, and I want to thank you all for coming. Thank you.